everyone! Thank you so much for watching another episode of the Weaviate Podcast. I'm super excited to welcome Philip Kiely. Philip is leading developer relations at Baseten, a company that's doing all sorts of exciting work around LLM inference and adapting to this new era of compound AI systems, compound AI system inference, and all the exciting things that come with that. Philip, thank you so much for joining the podcast.
Thanks so much for having me. I am super pumped to be here.
Awesome. So I think a cool topic to kick it off would be the state of the models, I suppose, like getting into kind of open source models are picking up. We have Llama 3.2, 3 billion, 1 billion parameter models. And so we have these smaller, super capable models, and just what's the state of, models?
What I'm seeing in open source is a couple different trends that I'm really excited about. So there's one trend toward the sort of everything model, a model that can do every modality, every topic, every language, everything you could possibly want all in one model. So if you look at the research that, say, OpenAI is doing with their GPT model family, you're looking at 4.0 and the real-time voice API, and you're seeing how they're trying to fit more and more modalities into a single model. Well, we're seeing that in open source as well, with Llama 3.2 having vision capabilities, Quen's got vision, Mistral's got vision, everyone's doing vision models now. We're also seeing more and more interest in voice, in speech synthesis, in audio transcription. The new Whisper model is great for that. So we're seeing a lot of interest in a single model that can do everything. But on the flip side, we're also seeing a lot of really cool stuff coming out with more niche specialty models. So that can be some of the smaller language models. It could be models for a specific task like math or code. It can be models for a specific language or a pair of languages. And it's also models for specific modalities. You know, you can have a model that does everything, voice, images, et cetera, but you can also have a model that's just for, speech to text, text to speech, image segmentation, all that kind of stuff. And so it's really interesting right now because there's so much development in both places. And we're starting to see some places where, you have some major pros to these everything models, you have some major cons. And on the flip side, the kind of opposite pros and cons list with the specialized models.
Yeah, super cool. I think like Llama having the open source vision language is super interesting. And obviously this, voice to voice with OpenAI and how you can have a conversation with it. Now I use it on my phone all the time. It's super cool to just talk to ChatGPT now. And I think also this notebook LM thing is a really big deal, being able to generate podcasts. And so is multimodal, is that kind of one of the big aspects that's interesting you the most right now?
Exactly. So it's where does that multimodality come from that's really interesting. You can have those multimodal capabilities built straight into the model, or you can kind of compose multiple models together that are each specialists at a single modality and get multimodal capabilities in your product that way.
Yeah, that's so cool. I really like this. I guess something that I really what I like to do is take PDF images and then parse it into text. And I'm in that camp compared to the cold poly. I know that's like a big one in the vector database one, but I really like this kind of like image to text. And then once I have the text, then I process it. But I guess something else that I'm seeing that's pretty interesting is like the structured outputs for multimodal. So I could give it an image and then it outputs following some structured output schema. So that's kind of an interesting one. Yeah.
Exactly. If you're composing multiple models together, one of the challenges that you're going to have to overcome is making sure that the input and output format is super consistent from call to call and from model to model. So there's a few different ways that you can go about implementing that. And the way that we've done it at Baseten is using something actually at the model server level. So the sort of naive approach here is you make a call to the model and you say like, hey, I want some JSON. And it probably gives you some JSON. And the fields are probably right. And if they're not, maybe you could just, go get a bigger, better model or fine tune it on more JSON or something. But at the inference time, really all you can do is just try again. Like say, hey, this is wrong. Can I get real JSON this time? Or can you correct this field or something? But that's not super reliable for these, mission critical programs that people are building on top of open source models. So instead, what we did is we looked at the model server level to actually constrain the output using something called outlines. So outlines is this great open source library. It lets you create a sort of state machine within the model server that is going to know at any given time what types of outputs are and are not valid based on a provided schema. And this schema can be pretty complicated. It has support for pretty much the entire Pydantic spec. So it's more than just a sort of basic JSON list. And with that, you apply something called token masking during the inference process. So as each token is generated, it's only going to be generated out of the tokens in the vocabulary that are valid based on the state that your state machine is provided. Because of that, the token validation process is basically instantaneous compared to the other more intensive parts of that next token inference. So you actually see basically the same tokens per second when you're doing structured output this way, and you get 100% accuracy. You're always going to have a valid output for your schema. And that's super critical because this way you're still building fast, reliable applications even with this structured output. And again, that's just a absolutely, table stakes essential thing for building any kind of multi-model system with AI.
Yeah, I have so much I want to say about this. I hope I can remember it all as I'm speaking. But this yeah, I give a quick shout out to Remy and Cameron from Outlines, and now building Dot Text AI and the work they're doing with constraint generation. It was really counterintuitive to me to see that this is actually faster, because I would think building the state machine,
Oh, there is
parsing.
a trade-off here that I should be explicit about, which is that process of building the state machine for a given schema does take time. It can actually take, 10, 20 seconds, in some cases even longer if your schema is really complicated. But it only takes time once, and then that can be cached in memory. So the first time you make an inference request with a given schema, your latency is going to spike like crazy because you have to generate the state machine. It's, once the inference gets started for that request and those tokens are getting generated, and then every subsequent request using the same schema, as long as it's kind of hot in the model, in the GPU memory, is going to be at the same speed that the original model inference was at. So there is that trade-off. And if every single request is going to be using a different schema, then obviously this trade-off isn't going to make sense for your use case.
Mm. Huh. Oh, that's a pretty interesting one there. With I guess we have at Weaviate, we're building something called generative feedback loops, where what we're doing is we're updating a prop. So generative feedback loops are about running an LLM over a massive collection of data, and we're updating some property or multiple properties. And so we have this one schema that then we do batch inference over. So maybe I think I might have missed this detail because of my use of it in that particular area, but I can see if you're doing single inference and you're always changing the output schema, maybe that sounds like a new problem. And then maybe there is something to JSON by prompting, which I think is pretty interesting. I've played a little bit with this where I've used the Opro prompt optimizer. Opro, if people aren't familiar, it's it's this really cool kind of evolutionary prompt optimization algorithm where the language model is sort of like the Bayesian model, I want to call it, where it takes a bunch of prompts and then it uses that in their scores, and it uses that to produce new prompts. And you can use this to, find the prompt that always outputs JSON. And so maybe there still is something to that approach. I think I think constraint generation, another talk from Remy from .text AI that I'll link in the description of this video is about how constraint generation even helps with in-context learning. There's all these other side effects that people are seeing from it, and helps with classification. There's this boost that people are seeing. So yeah, it does seem to me pretty clearly constraint generation is winning. You agree with that?
I agree. Constraint generation can have side effects like you talked about. It can affect reasoning and other things. But like you said, that use case where you described running a sort of high volume, high throughput batch process over the same schema is exactly what this sort of thing is designed for. And if you think about building a system that's going to compose multiple models together, that's going to have a interface with some API or some system that you've built on your backend, then you can imagine that the schemas are going to be a pretty fixed set where you're kind of generating data in the same format or same handful of formats over and over again. So that's definitely the use case that this sort of structured output is designed to facilitate.
Yeah, amazing. I think one other approach is that kind of natural language to format, where first you just generate the response in an unstructured way, and then the next call to the language model like cleans it up into the schema. And that's maybe for people tuning into the Weaviate podcast. I've also invited Z from the Let Me Speak Freely paper, and so we'll continue that one there. But Philip, I really want to dive now into, maybe we could even transition from to compound AI systems by discussing the role that structured outputs has in compound AI systems.
Absolutely. So, as a quick definition, compound AI is a term that's gaining more and more popularity to describe exactly what we've been talking about to this point, which is the jump from a sort of basic GPT wrapper type system where you just have a language model and you call the model and you get the response back. Or you have, say, a transcription model and you call the model and you get the transcript and then you post it as your podcast description or something. These single model inference loops are super valuable. Don't get me wrong, you can build awesome stuff by just calling a single model because these models are incredibly capable and get more and more capable all the time. But what we're seeing with our customers and the sort of AI native applications that they're building is increasingly they're composing multiple models, multiple steps. They're adding conditional execution, they're adding business logic, they're adding stuff like chunking. You know, a great example of this is Whisper can only process 30-second chunks. So you have to chunk up your audio files, run it through in parallel, stitch it all back together. All these sort of things, from those sort of basic engineering things around, okay, how do I just process this audio file more efficiently, all the way up to how do I build these super effective RAG systems? How do I connect, looking back to what we were talking about before, there's this idea of you have small focused models versus big models that do everything. So how can I potentially compose multiple small focused models to get higher performance or lower cost inference? There's all sorts of reasons that you might want to build a real pipeline out of multiple models and put that into your product. And the general practices around that are often now being referred to collectively as compound AI.
Yeah, and I think that the nugget about using smaller models and pairing them with this constrained generation is super powerful, because back when Llama 3.18b was, it kind of used to be like before this 3.2, like slightly different, but like having the constrained generation just really helps you plug in these small models, and is really enabling a lot of this. Yeah, and I think there's a lot of nuggets here. We had a podcast with Jason Liu, who created an instructor, and he explained things like say the task is re-ranking and you're outputting a list of IDs, and the structure, so you can kind of already start sorting a document. And there's like kind of like some streaming stuff you can do with this structure. And then I think with chain of thought, always adding like a rationale or explanation is like kind of like a secondary attribute that you're always producing in addition to anything you're generating. I think that's just super powerful. But yes, I think it would be great to kind of transition into compound AI systems and maybe broad perspectives. I guess to me, something that's very interesting is this kind of like ensembling inference. Like we have this new perspective now. I think, O1 from OpenAI really has got a lot of people thinking like this, where it's like, uh, you know, just either whether it's in a tree search structure or if it's just at each kind of step along your compound AI system, you're going to sample, say, 30 inferences and do some sort of ensembling. Are these the kind of compound AI systems you're seeing in you? Like what kind of, sorry that I dove right into that particular angle, but like what kind of compound AI systems are you seeing out there?
You definitely can build systems off of repeat inference to the same model. What I'm seeing a lot of today is using compound AI to introduce multimodality at a more efficient way than the sort of big everything multimodal models. So let's take voice mode, for example. If you want to do real time voice, you could pick up a model that does real-time voice via that API that OpenAI released. And I'm sure over time that model is going to get faster and it's going to get cheaper and it's going to get better, just like every AI model does. But right now, that's a pretty expensive way to do voice. What you could do instead is you could compose three models into a pipeline. So you could take Whisper, for example. There's a brand new Whisper Turbo model that's got an 8x real-time factor versus their Whisper Large model. It's completely open source and licensed for commercial use, and it's a highly accurate speech transcription model. So you could take something like that, and you can run that on a T4, an A10, an L4, all very cheap, cost efficient, very fast GPUs for this kind of model. And you can, run your transcription in a few dozens or a couple hundred milliseconds. And then you can take a language model and you can kind of stream that through it along with the prompt. And then you can take a dedicated speech synthesis model. You could use an API. We have this customer, Rhyme Labs, that makes an amazing speech synthesis API with 200 different super lifelike voices. So you can use an API like that. You can use an open source model like Piper TTS. There's Kokwi. There's a ton of different text-to-speech models. And each one of these steps might only take, a couple hundred milliseconds. There is, however, a whole ton of orchestration that has to go on around it. So it's really easy for this kind of thing to balloon up to like 3-4 seconds, and then you just don't have a good real-time speech experience. But if you're able to carefully orchestrate these model calls, if you're able to deploy all of these GPUs to like the same data center region, if you're able to avoid network overhead as you go from call to call, even at stuff like the DNS level, just making sure that all of your queries are routed within the same cluster versus going back out to the public web and having to do hairpinning there. There's a lot of model performance work and there's a lot of distributed infrastructure work that goes into this. But if you do all of that, you can actually get much better performance at a much lower cost by composing 3-4 different models for different modalities together versus taking a single model that just kind of does everything and throwing your work at that and letting it abstract away all of these problems that are also opportunities for optimization.
I'm just like maybe nerding out a bit too much, but this kind of idea of like in Kubernetes, you have some kind of like node, and you have a pod where you describe how much resources each of these like compute. It's basically like a Docker container. And so are you trying to, like, within one node, you could say have your 3 billion parameter Llama 3.2, your 300 million parameter Coakley text to speech, like you have all these models living on the same node, and then that's how you minimize sort of the network. Like the things like this go into it.
Well, the issue with that is if you're building this exact compound AI system or something like it, your different parts of the system are probably going to want to scale to different degrees and at different times. So perhaps you are building something for you're building something for a doctor's office where it's going to listen to the whole conversation and only talk occasionally. Well, then it's going to need a lot of whisper transcription and only a little bit of speech synthesis. Or maybe it's the other way around, where you're going to, briefly prompt it and it's going to give you long answers. You can also see traffic spikes in different parts of the system. You can see bottlenecks in different parts of the system. So the way that we like to do it is every model gets deployed individually. So every model has its own Docker container, its own dedicated GPU resources, and most critically, its own auto-scaling capabilities that are going to be traffic-based. So this way, maybe if it just so happens the way the traffic's flowing through, you might need 2 Whisper instances, 3 Llama instances, and 1 text-to-speech instance. Those are going to be able to all scale up and down independently, and that's going to help eliminate bottlenecks and also make sure that you're not paying for idle compute. So we do scale those separately, and then we do the work at the networking level to make sure that this approach of these separate deployments is not going to introduce a bunch of unnecessary overhead.
Yeah, super cool. And I really don't know too much about the like pod net bridge networking. I think is I don't even really know the words, but like I'm
To be
curious.
honest, me neither. That's the infrastructure team takes care of that, and I trust that they do a good job. But I've had the opportunity to talk to them in detail about it in the process of writing about it and learning about it, helping them prepare talks and blog posts and stuff. So it's a really fascinating topic and definitely something I'm learning more about.
Yeah, that's maybe even something that I like about the sort of LLM for all solutions kind of thing is that, then you're just scaling this one deployment, like, because there's a lot of hype about, smaller language models, build a smaller language model for the thing. But then I'm like, okay, how do you then deploy it? It's a little bit different. Like if I just have this one Llama, 3.2 that I'm just auto scaling, it sounds like an easier deployment to me. I guess that's kind of,
Yeah, exactly. There are some things that the biggest, best frontier models are absolutely necessary for. There's a reason why, as an industry, we keep making them and we keep making them bigger and bigger because you need those giant models for those cutting edge capabilities. But just like, every year the new iPhone comes out and then the iPhone non-Pro comes out and it's got all the same features as last year's Pro iPhone for less money. Well, kind of the same thing happens in models. So if you look at, for example, we've been talking about Llama 3.2, 1B, and 3B. Those both have function calling support, which is super great and kind of rare for small models historically. Well, a few months ago, function calling was brand new and only the biggest, best models, like Mixtral 8x22B was supporting function calling. And now you can get it in a 1 billion parameter model that runs on an iPhone from 3 or 4 years ago. So that sort of feature creep or feature cascading down from, I don't want to call it trickle down features, but maybe I should because this would go viral. But you get like trickle down features from the biggest frontier models into these small models. And if you can take advantage of that, that can cut your inference costs and your inference latencies substantially. Because no matter how good you get at running a giant model, you can get just as good at running a small one and use far fewer resources.
Yeah, super cool. I think there might even, well, I guess kind of just in deployments, and I'm just kind of thinking out loud here. I don't know, I'm not a super ex. We would like what we're doing is we just use, we use that the modal auto scaling and Llama 3.2 and then outlines as you mentioned, and that seems to work fantastic. But obviously, I'm very curious about the future of this kind of stuff. So I'm curious about like, we have mixture of experts models that maybe offer this, you know, specialized domains, maybe even multimodal mixture of experts is a thing. I'm not super aware, but and then we also have state space models, which seems like the thing. State space models are really great with long context inputs, and I could imagine like you mentioned like Llama 3.2, maybe it has this kind of like map reduce architecture where you're breaking up the inputs into these small units, but maybe you still have this kind of like hybrid model system where if it's a really long input, you still use your state space model. So I guess my question, Philip, is like, what do you think about like new model architectures? Is that maybe a way that models are differentiating themselves?
Yeah, new architectures bring new performance challenges. So those are always really exciting for us. I'll touch on a couple from that list that you mentioned. When you look at mixture of experts, the biggest challenge that we've seen with that is batching. So the way that mixture of experts work as a sort of overview for the audience is you have, say, in some cases, 8 different models within a single model, and only some set of those weights are going to be activated for each inference request. So I might make a inference request. It's going to hit 2, let's say, of the 8 sets of weights within that model. And because of that, because fewer active weights are used, less GPU memory bandwidth is used. That's generally the bottleneck on our inference process in terms of the tokens per second. And so by using this mixture of experts, we're able to get the capabilities of a much larger model with the performance of a much smaller model, which is awesome, right? That's a great architecture. The issue is, though, once you introduce batch inference to this process, because now if I'm making, say, 16 requests to the model at the same time, well, each of those requests is probably going to hit a different pair of experts. So I'm actually going to end up activating all of my experts during this batch inference process. There are still, of course, going to be benefits from this architecture, even with this batch inference, but those benefits are going to be much smaller than if I was just hitting the same couple experts with every request in my payload. So that's a great example of one architecture that it brings sort of a new challenge that needs to be overcome. Another great example is you were talking about long context. So, and there's something pretty interesting to look at there. So, as I mentioned earlier, the autoregressive phase of LLM inference is bound by GPU memory bandwidth. So that's, how quickly you can load the weights, the KV caches, the activations, the inference parameters through the GPU memory. And if you look at the prefill phase of inference, which is where you're taking the actual prompt itself and you're trying to compute that first token, that's actually in most cases going to be bound on CPU or GPU compute. So the number of flops that you're able to access is going to be your number one bottleneck there. Long context is interesting because it brings in both of those to that initial token generation step. And when you look at some of the upcoming GPUs, if you look at, say, like the H200 GPU, something interesting about that is it has more VRAM and it has higher VRAM bandwidth compared to, say, like an H100. So what I'm excited to find out is if these hardware optimizations could make a big difference for this long context, where perhaps the additional memory is going to enable faster inference when you have these really, really long input sequences. Another thing, of course, that's really interesting around this long context is the effects of quantization. We have some of these FP8 and coming up with Blackwell FP4 data formats that are allowing this GPU memory to be a little less of a bottleneck. So hopefully it's going to provide some pretty good benefits to long context inference as well. I guess one final thing I would want to talk about here in terms of architecture and in terms of how that affects performance is going to be KV cache reuse. If you have a multi-turn conversation, which is increasingly becoming standard, you have already computed most of the tokens in that conversation. And if you can reuse them, that's super valuable. So again, these sort of large GPUs that are coming onto the market, the H200s, the GH200s, and looking forward, of course, to the Blackwell generation, which I'm sure is going to just extend this trend. You see a really big potential for these, additional hardware resources to be used in a way that is compatible with these new architectural trends.
Super cool. So I think, I guess I don't know too much about that. I've been reading a bit about vLLM and understanding this kind of like internal, external memory fragmentation and about how you're usually like pre-allocating this memory that you're going to need for generation, even though it's going to be variable length outputs, and how they're doing optimizing that. And then things about like the way that this does concurrent requests, I think is really amazing. But yeah, I can't really hold a conversation too much on that topic. I guess my question would be like vLLM, like what's your sentiment on it? Just broadly, like what do you think about vLLM?
I think vLLM is great. We definitely use it a lot internally, especially for building these OpenAI compatible APIs and for building high performance model inference servers really quickly. What we use more, though, is TensorRT LLM. Are you familiar with it?
Yeah.
Yeah, so it's, for the audience, it's a inference optimization framework by NVIDIA that's specifically for LLMs, although we also use it quite a bit for Whisper because Whisper has a structure that's effectively the same as an LLM. The way that TensorRT LLM differs from vLLM is that it creates sort of optimized CUDA instructions for a given model through something called the engine building process. So you get a TensorRT LLM engine that's going to be optimized for a specific GPU and a specific model. So if I build an engine for, say, Llama 70B on an H100, or, well, it would need to be a set of H100s, then I can't take that and just run it on some A100s. I'd have to rebuild an engine for those A100s. But the benefits you get here are some pretty substantial performance improvements. We've even seen a number of favorable benchmarks in internal testing versus some vLLM engines, and we especially see that on the new Hopper H100 GPUs. I'm super excited for the Blackwell generation because I think it's going to offer even more architectural features for it to take advantage of. But yeah, I mean, no one really knows their GPUs as well as NVIDIA does. And so while the developer experience of using TensorRT LLM can come with a bit of a learning curve, we've built a bunch of tooling internally to make that easier. We have this engine builder that I gave it to the sales team, and now those guys are building engines themselves because it's just a config file. So yeah, it's a great it's a great system, the TensorRT LLM system, and the Triton inference server that goes with it, that we've invested very heavily in getting good at and figuring out how to make more broadly accessible. So yeah, I really like vLLM. I think it's a great project. But for the absolute highest performance use cases, I generally turn to TensorRT LLM instead, due to the amount of experience and tooling that we've built up with it.
Oh, yeah.
Also, TensorRT LLM does the batching part really well. It does this in-flight batching, where as soon as the last request is done, it slots in the next request and just starts generating tokens. It's a very efficient batching system.
Yeah, super cool. And I guess maybe my next question would be about like kind of like Ray and then this kind of like distributing across worker, like this, like you have workers. Is that something else that interests you?
So Ray is a model serving framework by Anyscale, which is a competitor of ours. We have our own alternative framework called Truss, which is open source and lets you build a model server with a Python file and a YAML config file. So personally, I don't even know how to do Hello World in Docker. I don't even know what Hello World equivalent really would be in it. I have it installed in my computer so that I can run the local development environments and stuff. But I'm far from an expert on containerization. So the way that I use Truss is I'm able to just write some Python code with transformers and other tools that I'm familiar with. And then it kind of handles the packaging that up into a Docker container. That Docker container then goes up on Baseten, which handles the distributed infrastructure part for me. So that's kind of the role of a framework like Ray. You also have Cog from Replicate is another one like that. You have Bento ML, you have MLflow. So a lot of different companies have kind of built their own solution for, I have some model weights and some Python serving code, and I need to turn that into a Docker image, and I need to get that Docker image onto Kubernetes. Truss is our answer in that world.
Super cool. So I think all that is super compelling on, yeah, understanding all these optimizations that are going into serving LLMs, and I really like that nugget about TensorRT. It kind of coming back to that thing we were talking about earlier with the smaller language models. I can imagine these optimization frameworks that create like some 100 million parameter transformer model, or maybe it's like a Robert, or like maybe it's just like GPT. I'm not. I know like sequence to sequence, encoder decoder, that kind of thing. Is probably that particular kind of model, but anyways, what I'm trying to say is you have some smaller custom model, and now you build it, you compile it, say, to this particular GPU, and you get more, throughput and that kind of thing through that. I know. So I really want to pivot topics back into the compound AI system world. So it sounds like, great attention to how we're going to run batch inference, how we're going to run tons of inferences and serve smaller models. And so I'm just curious about, your thoughts on the sort of like paradigm of compound AI systems. Like something that I always use as my personal frame of reference about it is if you're going to write a blog post with an LLM, first thing you do is you take a topic and you do web retrieval, and then you break it into say 5 topics, and then each topic in parallel you'll do more web retrieval, write a paragraph, then you'll assemble these 5 paragraphs into a like a rough draft, and then you'll proofread it, and now you've got your blog post. So that's kind of like how I think about compound AI systems. So yeah, could you tell me about like your perspective on compound AI systems?
Yeah, I think that, the performance aspect really comes in there because if you are trying to build this multi-step system, then the latency of every single step needs to get hammered out, or it's all going to add up, and then your blog post is going to take a long time to write. What I think about with compound AI is I just want to unlock capabilities that don't make sense to put in the model, or that aren't efficient to put in the model, or that aren't possible to put in the model. So the number one thing there is obviously, your data. RAG is the definitive compound AI system. It's the sort of number one used in production system today. And of course, the idea is, how do we supply real-time data to large language models? So I can kind of extend the how do we provide X to Y thinking to the entirety of compound AI. So you can make a compound AI system like we've talked about before for modalities. That's, how do I extend vision, or how do I extend speech? How do I extend video to large language models, to image models? And then there's also just compound AI in terms of, how do I build more capabilities into the model? You see that a lot with image generation models, with stuff like Comfy UI, where, Stable Diffusion itself and models like it are already pipelines where you have the different steps. You've got the encoder, you've got the UNet, you've got the VAE, you've got the step that brings it from the latent space back to the pixel space, the diffusers, all that sort of stuff. So with those pipelines, people, introduce new steps in there for stuff like masks, stuff like control nets. And those are, I think, also examples of compound AI systems where you're putting more than one model in together. So yeah, that's, to summarize, the way that I think about compound AI is, I use compound AI to introduce a new capability that the base model can't have itself, and doesn't make sense to just fine tune into the base model.
Yeah, this really inspires my thinking about like agents, like agentic systems, and how that differs from compound AI systems. And yeah, I'm actually developing the same kind of perspective about, so you have this agent interface where maybe it's something like a React prompt, or like, particularly how generally agent I take to mean like, it has a function schema, and one of these functions could be another model, right? Like it could be inference from another model. It could be like one of the steps. I think kind of like the DSPy perspective on compound AI systems is like, particularly what these five steps are going to be, and you're going to always be doing these five steps. And so you have this really great way of thinking about, this is always going to be, say, the workflow, like that. I think early days of like LangChain and like this, people were calling it workflows all the time. How do I come up with workflows in my life, and that I can break into multiple language model calls? And once you always know the same thing, but then this agent interface is more flexible. Like you might do this 5-step thing, but could be like, just one of the things it does, sort of, is like how I think about it. Yeah, I'd love to ask you just like how you think about agents and their connection to compound AI systems.
I think that compound AI is a way of architecting your code. It's a way of
Yeah.
composing multiple models together without introducing latency overhead, without introducing errors, and with introducing new capabilities, and with adding in the ability to do business logic, conditional execution, that kind of stuff. So obviously, agents are probably the number one use case, maybe number two after RAG right now, for this kind of architectural system. So I definitely think about it as, compound AI is a way of building a system, and agents are the things that you might build. And one way you can see that, kind of intuitively, is if you look at mapping out the architecture for a compound AI system. It basically looks like a graph. There's nodes and edges. And if you look at any sort of complicated agent system, it's also a graph. So the compound AI world of performance optimization and infrastructure optimization and error prevention and that kind of stuff, I think, is just the engineering layer that allows agents to be built, and built to be fast and reliable.
Yeah, It kind of like with DSPy, it has this analog to PyTorch, and it's got this kind of you're writing the logic of the forward pass, and say you have one call that's going to be taking as input three tool calls, three function calls, and so by writing it out explicitly like that, you have better chances to parallelize the calls to the external tools, or if say this graph thing where it branches and then the model inferences are going to like maybe it's like the Monte Carlo tree search thing where we're going to plan and then we're going to be unrolling our pass down the tree totally in isolation of each other. Then later on, we'll, come back together. Yeah, it does sound like, yeah, I think I'm coming to the same conclusion where that sounds more efficient than the agent interface, where again, I find this agent interface to mean that you kind of have this like, it's sort of like this auto GPT idea of like, hey, am I finished yet? No, I'm not finished yet. Let me do these three things and then assess again if I'm finished or not. So it's got this like more open-ended interface. It's like more flexible to adapt to any type of problem. But then it's like, and I had read this paper from Carnegie Mellon. It's called agentic. It's called like agent workflow memory. That's kind of about how you bring like in context learning of workflows into that agent interface. So it would have like some examples of like multi-stage. Hey, like I had to book an Uber. So first I did this and this, and that worked. And like then I had to do another task. And so here's my example for the in context learner trajectory. But yeah, I think what you're saying about the optimization you make when you explicitly design it out into a compound AI system seems pretty. I think, yeah. I guess I'm still on the fence with that one.
Another place, just based on what you were saying, where compound AI really helps there is that function calling step. So personally, I think function calling is actually a really bad name for what's going on because the LLM in the next token inference environment can't actually call a function. I personally think of it as more function selection. I provide the model a set of functions with a description of what each one of them does, and it tells me which one it wants to do. But then something has to actually go execute that. And that's where a compound AI system, where every node is able to scale independently, makes a lot of sense because then you can kind of have a second you can have a Docker image for each function that you might call if there are different models that you want to run inference on, or you can have just a basic serverless CPU type thing spun up for making API calls to say like the Uber API to book an Uber, like you just said. And so the LLM is really only responsible for selecting the function. The compound AI system in general is responsible for providing the capabilities of actually executing the function that was selected. And that's just another place where this compound AI approach to building multi-model, multi-step systems kind of seamlessly enables you to build agents because you don't have to go from this model influence world to this more traditional software engineering world. They're just seamlessly blended together.
Yeah, I think I guess quickly on the function calling thing, I guess the only thing about that I do like about function calling is because you also have to format the arguments correctly. And I went on this rabbit hole with like the Gorilla research from Berkeley, and we were doing like some text to SQL style work with Weaviate's GraphQL API, and we kind of learned that like getting the perfect arguments, that there is a little bit to that. So I think there is like this select the tool, but then also use the tool correctly. So
That is true. And that's a place to go back to our description of structured output earlier. That's a
yeah.
place where our server side structured output is super useful because when we do return those function calls from models like Llama, we're providing those arguments to the function in this super predictable way that the system can just pick
Yeah.
up. But you're right. You're absolutely right that the model is responsible for choosing correct inputs and, like you said, using the tool appropriately. It's just that when I was first exposed to function calling a little while ago, I was super confused. Like, wait, how is it actually running the function? It can't run it there. So the idea of thinking of it as model selection or function selection was just a useful mental model for me to have as I kind of learned how it all works under the hood.
Yeah, I like that a lot too. With especially as we're talking about deployments and Dockerizing things, and yeah, executing the tool being a totally different problem. But then, okay, so this is kind of where I'm thinking about this compound AI system versus agent with respect to deployment. Is that like with my agent, like a lot of agents are benchmarked on like data sets like Web Arena, where it's like, earlier we discussed this compound AI system to write a blog post. It does those 4 steps, and that's an excellent way to write a blog post with LLMs. But if you want to also have this system be able to book you your Uber, now it's like now you're probably better off with the agent. Otherwise, you've got like two compound, because you can just deploy one agent, right? Compared to like two compound AI systems. And so I think maybe that's something that comes in a bit. Like the agent deployment sounds easier to me.
I think that no matter how you conceptualize it, you do have to deploy a explicit capability for each one of these things. So you have your each model that the system is able to access deployed separately. You have the business logic, you have the serverless inference of the API or serverless calls to the APIs that you might want to give the model public access to. You have, I think, also something we've really missed here in this conversation is you probably want to have some conditional execution logic that might include a human in the loop element where you're going to send a Slack message with human layer or whatever to be able to get approval to take certain steps. When I think about deploying one system versus deploying two systems with all of that, though, I think more about you know deploying each component of the system in a way that lets me write pretty minimal code to weave them together rather than trying to make a single monolithic deployment of a system or two deployments of different monoliths. I've got my blog post monolith and I've got my Uber call monolith. I think a lot more about how do I build myself a set of auto scaling endpoints for these different capabilities and then write sort of a simple wrapper layer on top of it that's able to take a path through all of these things versus having to kind of hard code everything in together.
Amazing. And kind of, I guess one other thing about the execution of, like, mentioned the human in the loop thing, that just sparked a lot for me to think about sending the Slack message. And I'm curious what you think about, like Llama Index has workflows that they're branding of this kind of agent processing, that generative feedback loop thing we're working on at Weaviate that has a task queue behind it. And I'm curious what you think about these task queues. Task queues are basically a way to kind of like ensure reliability, ensure that every step of this software process indeed does get executed. And just like, as I've been learning about task queues, it's like quite a software industry around this kind of thing. I'm curious what you think about, like, using task queues to make sure the compound AI system reliably executes. And
To be honest, I haven't really heard of task queues, and I'm not going to go on a podcast and just yap about something I'm not super familiar with. I would love to learn more, though. So, is the idea that as your agentic system executes the tasks that it's given, it creates a set of approvals that it's going to ask you to go through one at a time, or am I misunderstanding how this task queue system works?
yeah, and I would also say, but by saying like, pretty much with the generative feedback loop system, it's about, we are running an LM inference over a massive collection of data and we're, and then we're writing it. And so you basically, the task queue is just like the batches of data. But and
Oh, okay. So it's a queue of tasks that you're building for your agent to execute.
yeah, so I can imagine like an agent comes up with a 20-step plan, or obviously compound AI systems, you're breaking it up into, yeah.
Right. So the agent comes up with a bunch of tasks that then get placed in a queue and executed one after another.
Yeah, basically.
Gotcha. So one thing that we've built for that is like async inference, where you can make a promise and then check a webhook.
Yeah.
That's something that I think is going to be really important for these queue based workloads. But the other thing I would say is within reason, obviously, you don't want to just spin up infinite computers because, I don't know about you, but I certainly don't have infinite money. I do like to think about ways to process queues in parallel rather than just waiting and doing it one at a time. That's where sort of being able to flexibly scale the different parts of your system comes in. And obviously, if each step in the queue perhaps relies on the previous results, that's where a more queue-based system could make sense. Maybe that's where you start to do asynchronous stuff if your tasks are quite long. But if I want to, say, as we've been talking about, write a blog post and there's 4 separate sections that don't really interface with each other until the end, well, I want those 4 sections to be written in parallel. I don't want a queue doing that. So that's, again, where having independent scaling of every step within your compound AI system is absolutely critical.
Yeah, amazing. There's another paper called Alto that I'll link in the description. I'm not super familiar, but yeah, there's a lot of these optimizations you can do when you know this compound. So you know the 4 steps of the blog post writer, scale each component separately. Awesome. So Philip, kind of an anchoring question I wanted to ask about this compound AI system design is I was really inspired by this paper. Jeff Clune, I think is I don't remember all the authors, but I'm just a huge fan of Jeff Clune. So whatever he's publishing, I'm reading, and it's about meta agent search, which is basically about searching for compound AI systems. Like we mentioned, this that there's that 4-step to writing a blog post where first you take a topic, then you decompose it into, or you take an initial topic, you decompose it into an outline, then you write a paragraph, then you proofread it. But like searching for the decomposition of tasks, that feels like this really interesting like meta problem. And I'm curious if you've come across that kind of thinking, like, or just generally like how do people design compound AI systems? Really, is it like trial and error, or just kind of like intuition about how you might break down a task?
Again, the majority of the compound AI systems that I've personally worked with are more about introducing new capabilities to a model, introducing new modalities to a model, introducing, like, okay, I want to be able to process 10 hours of audio instead of 30 seconds of audio to a model. And so in those cases, I generally see the architecture, excuse me, I generally see the architecture as being based on the model capabilities. That's where we start. And then from there, we kind of address every single weakness with another step in the system. And I would imagine that approach would do well with agents as well. You can start with, what is the model really good at? Maybe it's really good at reasoning. Maybe it's really good at coming up with ideas. Maybe it's really good at looking at an image and seeing what's in it. And then you can add, add in what it's bad at. Maybe it's bad at spelling. Maybe it's bad at counting. Maybe it's bad at math. And introducing sort of corrections into that system to add these capabilities is overall the approach that I've seen work well, because rather than trying to take what the model's good at and bring that outside the model and work on it more, that doesn't really make sense. Instead, I've always seen these systems work best by taking what the model can't do, figuring out how to offer it to the model, and then just letting the model kind of enjoy this access to this new capability.
Yeah, that's brilliant. I think like DSPy assertions kind of pioneers this in the DSPy world, and there's like some other thinking is like network of networks is a great another paper I'll link in the description about this kind of like verifying is easier. But it sounds like what you're on is kind of like searching for weaknesses in the model and then sort of developing. I want to call it like guardrails, but then it sounds like I think guardrails. I think like when people hear that term, they might think that you're either talking about like probably like the JSON thing is I think the most common initial use of that, but then it also might be like offensive language, things like that. I think are the common, but kind of searching for failure modes in the model and then having extra checks around that in the compound AI system. That sounds like a really fascinating area that I think is yeah.
Exactly. If we're going for language, for example, you could heavily reinforcement learn the model through the post training fine tuning process to make sure it doesn't do certain things, and you absolutely should do that. And then you can probably get to, I don't know, 99.99 whatever percent that it's not going to do that. But if you want to get to 100%, training the model and training the model and training the model probably isn't going to get you there. And even if it can, it won't be nearly as efficient as just wrapping your model call with a quick little regular expression that just makes sure those certain words that you don't want in your output are never there. Um, so it's interesting because some problems are really effectively solved at the model level, and some problems are really effectively solved outside of it. And it can sometimes be a little surprising what's best to solve where. But that's generally the best use for compound AI, is to kind of allow more specialization back into generative AI. Generative AI models are amazing because they're so generally capable. They can do anything, but they can't actually do literally everything. So introducing more of this specialization back in and letting models, individual generative models, more efficiently do what they're the absolute best at, composing those answers together and providing, ordinary code for stuff that doesn't really make sense to train into an LLM, like addition, subtraction, that kind of stuff, is, I think, the way to go to build highly capable agentic systems, AI native applications, and anything else that you want to build around AI that's not just, a GPT wrapper.
Yeah. Awesome. Well, Philip, thank you so much for joining the podcast. This conversation has been amazing. It's really, opened my eyes about thinking about the specialization offered by compound AI systems, the optimizations we can make under the hood to run them more efficiently. And yeah, I think this kind of designing some particular compound AI system versus open-ended agent interface, I think this is just one of the most interesting topics out there. And yeah, all sorts of cool things I'm looking forward to of our collaborations with Baseten and Weaviate. I definitely can see things like using the Weaviate database APIs as a tool in Baseten. And then I'm also really excited to explore within our generative feedback loops. We want to offer some kind of optimized function. Like we're trying to design generative feedback loops to be, I would like to call this like declarative, where you say, I have this collection of blog posts and I want a summary. I don't care about how you do it. And then under the hood, maybe we could use some Baseten inference optimizations and develop all these cool things. So Phil, definitely looking forward to future collaborations. And thanks again for joining the podcast.
Absolutely. Thanks so much for having me, and I'm looking forward to working together more in the future.